So about that Arduino-based torch light controller of mine, here's the pile of Arduinos I killed in the making of that. One of them was back when I was still breadboarding, and I changed the firmware to use the internal analog reference voltage, while I still had an external power applied to that pin. So when I plugged it back in after updating the firmware, it immediately killed the ADC. Another one I soldered onto a old version of the current board that had a problem on it, and my attempt to desolder it didn't go so well. Another two of them I plugged into the current version of the board backwards by mistake and fried them that way. Another one I got some water on, and that killed that. And the last one, I don't really know. But I can't upload firmware to it anymore, so I did something that must have killed it. Yeah, and that is why you buy, one or two official Arduinos to help support the project and, kick some money to the guys who came up with these. And for the rest of them, you buy the cheap Chinesium ones, because when you're doing this kind of work, you're gonna fuck up. And then, yeah, these guys are all pretty well dead, so may as well. So here's version 1.0 of the THC. It's the first working version, the current version, and the one I demoed about a month ago. So I haven't done any of the changes or progress to it since then. It's what you saw, and it does work as shown with my setup. Now, as for your setup, your mileage may vary. I'm not gonna lie, some things on this board do depend on other parts of your CNC system. For example, what plasma cutter do you have? And does that plasma cutter have a voltage divider built in or not? It kind of matters, right? Like, does your plasma put out a whole bunch of EMI and interference that'll mess with the Arduino? Because if it does, you'll need more shielding than the no shielding I have here, right? All these things do play a role. But what I hope to do in this video is cover this in broad enough terms that you have the general gist of what every part on this board is for, and why I picked it. And I can also cover it all in enough, close-up specific detail that you can copy this thing exactly if you so choose. Or you can make slight tweaks to it if your situation is similar but not exactly the same as mine. Or you can use the general knowledge you gained to make something entirely from scratch of your own. If you do either of those last two, I would also encourage you to make a video of your own, or post something on GitHub, and just share the information, for your design with other people. So over time, you can make a small library of different designs of THC that work with different plasma cutters and different CNC systems, etc. So over time, we can all get, better tables for ourselves. Like AVE says, you make cool shit and put it on the internet. The way I designed this PCB was definitely overkill, but for me, I used it basically as a learning experience. I designed it in the EDA program, took that schematic I came up with, and then put that on my K40 laser, and used that to etch the mask on a piece of this FR4 single-sided copper-clad board, and then use ferric chloride to etch away the excess copper, drill the holes, solder it up, all that. It's a lot of work and definitely overkill if you're only doing a one-off prototype for your home shop, okay? So if you're doing just that one-off, what I'd probably recommend is doing a schematic on paper, then breadboarding it, make sure it works on the breadboard, and then solder it up on a piece of perf board. Basically, it's the FR4 with copper on one side, but instead of having a solid sheet of copper, it's just a bunch of little rings. And you can make either solder lines along those rings or put jumpers in, all that. And it's just going to be a lot faster and a lot easier than messing with all the other software. But if you want to go whole hog and learn the software and all that jazz, you definitely can, as demonstrated here, right? For the program, I used KiCAD, which is a free and open source EDA program. EDA basically being the PCB variant of CAD, okay? So first time using it, it went pretty smoothly. I kind of blundered my way through the program and still came out with a functional product at the end. So you can't really ask for more than that, right? And yeah, KiCAD was easy to install, didn't crash at all when it ran. It was very smooth. All the menus made sense. The steps in the process were all very clear. And yeah, it was overall a very good experience. And if you want to come up with the schematic and then send that off to like a real PCB manufacturer and get a whole stack of boards you can solder up and turn into a real sellable product, then KiCAD is probably a good one to learn. Now, I learned it by watching the Get Into Blinky tutorial series elsewhere here on YouTube by the channel Contextual Electronics. So he had a series called Get Into Blinky 4.0. That was for the slightly older version of KiCAD, 4.0, whereas I was using 5.1. But there weren't enough changes to make a big difference. I still would follow along and it still made sense. But I even noticed that just like 2 days ago, Contextual Electronics began publishing Gaiden the Blinky 5.0, which I imagine is for the newer version of KiCAD. So if you do want to learn and go all out, you're in luck because, yeah, it's a very good tutorial series and will teach you the ins and outs of all that jazz. Now, I'm going to make the wiring diagram and schematic I came up with in KiCAD available, but I'm not sure I'm going to publish the whole project file, just because, again, I am a total novice with it, and I'm pretty sure I did some things not the right way. And then the whole the wiring diagram too, it depends on stuff, like this LCD and the potentiometer and parts like that. And these guys just came from my parts bin. They've been sitting there for 2, 3, 4, 5 years. I have no idea where they came from or what make, model, brand, whatever they are. They're just random parts that's sitting around that I figured out the wiring for and put in this project because I had them sitting around. If you go on Amazon or eBay or whatever, or DigiKey, Mouser, and order your own LCD, it'll probably have different wiring, which means your wiring diagram and footprint are going to be different. And then when I had my project file and actually tried to transfer that from my desktop to my laptop, it wouldn't load correctly anymore because I'd seemingly saved the footprint files for this and this in the wrong place. Again, things I'm learning because I'm a novice at KiCAD. Maybe at some point I'll clean that up and then get that published too. But for the time being, the schematic and the wiring as I publish it, and the overview in the video here are really the main things you should follow along with. So for the super high level look at how THCs work, they basically read the plasma arc voltage off the plasma torch, compare that to a set point, and then send signals to your CNC controller saying either move the torch up or down until the arc voltage matches your set point. So due to the way the physics of plasmas work, basically the higher your torch tip is above the work surface, the higher the arc voltage is as well. So given that the cutting height is very important for keeping a good cut quality, and the fact that there's a positive correlation between the voltage and the cut height, you can measure the voltage to keep your cut height in the right range for getting the best cut. So it's good for, basically anyone to have a THC on their CNC plasma cutter. It is a feature you really do want. It does make it work a lot better. Now, if you're lucky, the manufacturer of your plasma cutter will have tables in the back of the manual saying what the ideal cut height is for a given material and what the corresponding arc voltage for that is. So I have a Hypertherm PowerMax 65, and going off the top of my head, I think as one example, for 1/4 inch plate cut at 45 amps, for the best cut quality, you cut at 45 inches per minute, and the cut height should be 0.06 inches above the plate. So just barely skating above the plate. And that corresponds to an arc voltage of, I think, 135. I might have numbers fuzzy, but that's the gist of it. If you don't have that in your manual, basically just test it, and then see what works the best, right? Try it at different voltages, using a different set point each time, and see what ends up giving the best cut quality. In fact, even if you have the tables, that just gives you a starting point. So you know roughly where to begin, and even still, you should run some tests and see for your machine what ends up giving you the best cut quality. Then when you have it, write the number down in terms of the amperage, the inches per minute, all that for a given material and thickness. And then next time you run that material, use the same numbers you already tested, right? Now again, because I'm using the PowerMax 65, it has a voltage divider built in. So the arc voltage in the plasma goes up to 300 volts DC. Usually it's about 125, like most materials are in that rough range, at least like 100 to 150. It'll be in that ballpark, but it can be as high as 300 volts DC. That is not the best, for reading directly, because 300 volts DC is a lot of volts. It's potentially lethal for one, and it also would fry a lot of electronics. Like a little Arduino, it can't read 300 volts DC. So Hypertherm luckily includes a voltage divider in the machine that steps it down 50 to 1. Okay, so what used to read between 0 and 300 now reads between 0 and 6. Much safer, and the Arduino can read that without going up in smoke. definitely good. If you don't have a voltage divider built into your machine, then you're gonna have to add one on your board instead. It's, or you're probably gonna want to. Depending on how you do your circuit, you can do whatever you want, plenty of ways to skin this cat, but you probably want a voltage divider in that circuit. So in Hypertherm's case, you've got 2 pins on the back of the machine, which I forget which 2 they are, but some of the manual, one of them is the arc voltage plus and one is the arc voltage minus. In reality, the way a plasma cutter works, the ground clamp is actually the positive end and the electrode is the negative end, but it's not super critical for this application. The more important thing is you treat your negative one as ground and the positive one as the thing you want to read. So if you are doing a cut with your plasma cutter and you just read between those 2 pins with your multimeter set to volts DC, you'll read something about 2.5 because 2.5 times 50 is 125. Like I said, most cuts are in that range. Now, if you want to know how the voltage divider here works, you should be familiar with a few circuit basics already. For example, Ohm's law, like V equals IR, that's pretty important. Then the formulas for resistors. If you have 2 resistors in parallel, right, or 2 resistors in series, the resistance in series equals resistor, the first resistance plus the second one, just added straight as if they're 1. If you have them in parallel, then you take 1 over the first resistor plus 1 over the second resistor equals 1 over the equivalent resistance of the 2 in parallel, right? I'm hoping these are formulas you know. If not, there'll be Wikipedia links below, and you probably got some learning to do if you're going to embark on this project on your own. But for Hypertherms, if we have the machine turned off and we just read between the 2 pins on the back of the machine, we can read that it's 2 kiloohms on that 1 resistor in the divider circuit. So from that, we know it's 50-to-1 drop. So to be pedantic, the first resistor in that should be 98 kiloohms, and that would give you an exactly 50-to-1 drop. In reality, it's probably 100 kiloohms, just guessing, 100 kiloohms is a nice round number. It's probably an easy part to get, whereas a 98 kilohm resistor is probably not as easy to get. But it's still close enough to 50-to-1. We can, just call it that and still work from that anyway. So we have this divider. It puts out a much better voltage for us to read. We can read it with the multimeter. Great. Now, how do we work with that on the Arduino circuit and the THC? Well, that's where we begin running into problems, right? Because the multimeter, it has some filtering and smoothing and things built in. So the voltage you read here comes out rock solid as like 2.5 or 2.62 or whatever you're cutting at, right? It'll be a very steady reading. In reality, that plasma voltage is actually jumping all over in that range. Because the way plasma cutter works, there's just a whole bunch of switching and things inside, and all that makes electrical noise that you need to filter out in your circuit to let the Arduino read it at least well enough for your THC to work. So for that, we use what's called a low-pass filter. So it takes the higher frequency jitter in the voltage and throws that out and lets the lower frequency things pass. So if the voltage is mostly steady, we read something that's mostly steady, right? If there's a bunch of like high frequency noise in that, we only read the underlying steady parts. So the most basic low pass filter is called the RC circuit, right? It has a resistor and a capacitor in it. And basically the way that works is you got the voltage input and you're reading the output down here. And when your input signal, varies to the high side by a little bit, the capacitor has a capacity for storing the excess charge. And then when the voltage input goes low a little bit in that high frequency noise, the capacitor can output some extra charge and help bring it back towards the average. So it just does some smoothing on, on that voltage there. So your output here reads more steadily. So that is what the capacitor here on the board is for. Now, you might notice this is an RC circuit, right? If you look here closely, you don't see any resistors in this area. So where is the R in the RC? Well, that's when you get into some more advanced electrical engineering and doing things like, real analysis and network theory and Thevenin's theorem and stuff like that. And that kind of gets beyond the scope of this video. I would point you towards a few resources if you want to learn more about that. Again, links below, Wikipedia, that kind of stuff. There's also a very good YouTube channel called the EEV blog, run by some funny Aussie bloke. Goes over everything electrical engineering, great detail, great entertaining and educational. There's also a YouTube channel called All About Electronics, which is very good, lecture type presentations. The guy who does those ones has a very, very thick Indian accent, but if you can get past the accent, the content is top notch, okay? And he'll walk you all the way down from the basic stuff like Ohm's law, the V equals IR here, until Thevenin's theorem, and you can see how a voltage resistor like this ends up actually being an equivalent resistor on the circuit, okay? So, yeah, basically the fact that we're reading, this voltage in our low pass filter is the voltage out from the plasma cutter. And we've already got two resistors in the circuit, going between the 300 volts DC plasma and the ground, with the out being right here. So these two resistors end up, there's an equivalent way you can describe them using Thevenin's theorem as a single resistor with the voltage input here being on that 0 to 6 range. So in reality, the equivalent Thevenin resistance of these two in the divider ends up being the same as the formula for resistors in parallel. It's kind of complicated, but trust me, there's some math and stuff behind it, and that's the way it works. So you'd end up not needing a resistor on this board here for our RC circuit because the resistor is already built into the plasma cutter. And now, picking the values of our RC filter, they come into play with determining how fast the filter responds and what frequency it filters out. So if you have like a very large resistor and a very large capacitor, then it ends up taking a longer time for your RC circuit to respond, right? Like it moves slowly because it has a bigger capacitor to fill and it holds more charge and stuff like that. And we want to filter out things that are very fast, but we don't want to make the filter, itself respond too slowly. Otherwise, it makes it hard for the THC to respond in time, when things are really changing, right? When the plate is actually sloped, right? When the plate does not sit level to the gantry and the torch is legitimately getting closer to the plate and getting nearer to crashing, we want our Arduino to be able to measure that quickly and be able to respond. Even if it has more noise in the signal, the way we send our signals to LinuxCNC or Mach or whatever to tell it to move up and down, if there's some noise in that, that's okay because the up and down signals in the end will kind of cancel out, as we'll see when it gets to the software and more operation in the next video. But yeah, so we want to have it be a relatively fast responding filter. And there are calculators you can use and formulas for determining how fast a filter responds. Now the resistance value here, we can't pick because that depends on the voltage divider, right? This is calculated from these two and those are both set in this 51 divider. But what we can do is change the capacitor value. So you either use some calculators online or you do what I did and do empirical engineering. So you see here this capacitor in the series or circuit. It just plugs in, right? I took a capacitor, I cut the leads so they fit this plug here a bit better, and just gently tinned the legs of it here to have a better fit. And I tried different values, and 10 microfarads seemed to work. Like it came out with minimal jitter, but still responded with good time. And if you go in the RC filter calculators and you plug in one with, let's see, Thevenin's resistance for this is equivalent to the parallel resistance of this. Since this is 2 kilo ohms, this is 100 kilo ohms. That's going to be about, probably 1.8 kilo ohms or so. So if you do the math on a 1.8 kilo ohm resistor and a 10 microfarad capacitor, it ends up responding in, I think, 0.05 seconds or something. It's relatively quick, at least for our purposes. So here we have the voltage input from the plasma. There's the resistor already, we get from our voltage divider. At that point then, we put that out to the Arduino's analog pin. We have our capacitor. That goes to ground on one of the legs. And then the plasma's negative terminal and the Arduino's ground are also all tied to the same ground on this board. Whew. Hope that makes sense. Got a little bit advanced, but at least with that overview, you might get how this works, or at least have the keywords to search along. Read some more in the links below. I do have a degree in physics. It's kind of old, haven't used it in a long time, but at least it was a good leg up when it came to learning this stuff. If you don't have that, it'll take you a little bit longer to learn. But if you've done any work with electronics and stuff, or or even like a sophomore in EE, probably understands this pretty well. So if you don't get this and you have questions and things, you can ask me. I might be able to help you in the comments below. Or if you got like a nephew who's in an EE program in college, that'd be the guy. He probably knows even better than me, to be honest. Anyway, yeah, that's how we get the voltage conditioned well enough that the Arduino can read it. So with that, let's move on to all the other things on the board here. Now that we covered that low pass filter and the capacitor here, basically everything else on the board should be pretty straightforward, okay? Like down here, we have a bunch of screw terminals, and all those do is connect stuff that's off the board, stuff that's on the board, right? Very straightforward. So like here we've got the DC input power for the board, so 12 volts positive, and then the ground. Those go to a barrel plug over here, and that I hook up to this one on this ATX power supply to provide the 12 volts. Now we'll talk about this a bit more in just a sec. Over here we have screw terminals for the plasma, so the negative and the positive. That negative one is tied to ground, and the positive one has the filter and capacitor here, and also goes to the analog read pins on the Arduino over here. And then over on this side, we have things that go to the parallel port breakout board on LinuxCNC for actually reading the up and down signals from this THC. The next important thing about this whole system is keeping a steady power supply to the Arduino so it can do good analog reads. Okay, I kind of showed this in an earlier video, I think about 2 months ago or so. It's been a while now, but basically the Arduino typically runs on 5 volts. You can power it with anything from like 4.5 to I think up to 32 volts. But if you give it a higher voltage, it has to drop that down to closer to the ballpark of 5 for this chip to operate. So there's a linear regulator on the bottom of this board here. So when you feed it 12 volts DC, like I was in that earlier video, the linear regulator basically wastes the excess electricity as heat to bring it down to the desired 5 volts for this board. Now when that linear regulator gets hot, it also gets erratic. So rather than reading out 5 volts rock solid, it ends up reading like 5.1, 5.02, 4.96 in different voltages. And the voltage of the system is what the Arduino uses by default as the analog reference for all the analog read pins. So if your reference voltage is being erratic, then even if the thing you're reading is steady, it will give you erratic readings. Imagine you hook a battery up to here rather than a plasma cutter, right? So a very steady DC voltage because it's a battery. That will still give you erratic readings if the reference voltage for your analog digital converter is itself erratic. So I showed in that one video, if I blew air on it with the air compressor and cooled it off with just a gentle gust of air, then that was making it get steady again. I have a better way of getting around that now, and that's firstly to feed this thing a better steady voltage, and secondly to apply an external voltage to the analog reference pin. So we're feeding the whole board off of 12 volts DC from this ATX power supply here. It's a Dell power supply. It came from an old desktop. I think this one was one I found on the curb, actually. Someone was throwing it out. I'm like, oh, a computer. The power supply probably works, so pick it up, take it home, take the power supply out, test it. Sure enough, it's good. The rest of it goes over to the electronics recycling place, and then this stays in the workshop until 2-3 years later, whenever it is now that I'm finally using it. Basically, these power supplies are going to be at least somewhat decent quality, and you can power them even without the computer by connecting to the pins there with a 10 kilo ohm resistor, and you'll find other guides online about how to do that. The long and short of it is you want to have a steady power supply to feed the board, and you want it to be more than 5 volts. So if you go on eBay and get the like Long Ding Dong brand power supply, that one probably won't be too steady. Its output voltage will be all over the place, and then that will end up kind of passing through to other parts of the system. So do yourself a favor, get a steady power supply, and it will save you a headache later on. Now, secondly, rather than using the Arduino's voltage as the voltage reference for its analog digital converter, I'm giving it an external voltage. So over here we have a linear regulator, like the one on the bottom of the Arduino, but much bigger and much better quality, much more steady. It's the LM, I think 317. It's a very, very common one. Yeah, LM317. We'll talk about all these part numbers more a bit later. But basically this one, you give it 2 resistors, and those are used to set how much of a step down you get. So I forget offhand what the output voltage of this is now, but I think for the 2 resistors I picked, it's like 4.5 or 4.7 volts or something. So it's not a full 5, but it still gives you a very, very steady voltage. And that means anything the analog digital converter is reading will be reading equally steady. Now, because the reference is only like 4.5 volts, it can only read things up to 4.5 volts, right? Hopefully you've done some Arduino programming by now, and you've already been familiarized with the analog read function. It returns 0 to 1023, and that is basically comparison between the voltage you're trying to read and the reference voltage. So for anything above 4.5, you'll just get 1023. It ends up clipping the signal and is telling you the same thing as if the voltage were 4.5. So if you're getting 6 volts here, which is the full 300 volts DC in the plasma cutter, we can't tell that on the Arduino. But that doesn't matter, because if you ever read a voltage that high, all that means is the torch is just way, way too high, right? It just means it's too high, because ideally your voltage readings will be about 2.5 for my whole setup, right? So if things are reading at 4.5, we just know lower the torch, lower the torch, lower the torch right fucking now. So I don't mind clipping a bit of the signal at the top end, because it should never be that high in the first place. Let's see. We've also got these 2 little capacitors here, which are recommended in the datasheet for the LM317, just as extra filtering on the input power it receives and the output power that it's giving here for the analog reference that the Arduino uses. Apart from that, we've got the potentiometer, which is used when this thing starts up. So it reads the 2 legs, the potentiometer, to see like how far along this is in the twist. And then I have a simple scaling function that converts that to a number in the range of roughly 100 volts to 150 volts, the operating range of your plasma cutter. It displays that setting on the LCD here, and once you set it, it locks in and just begins displaying the voltage read off of the inputs from over here. Now the signals for up and down, what you're trying to send to LinuxCNC is calculated on the Arduino with some very simple code, right? It's comparing the reading here, the set point you'd set over here, okay? Like I said before, it's pretty simple. And then it outputs on 2 of its digital pins either a signal for up or down. And that comes over here to these optocouplers. So we have resistors in line with the optocouplers, simply so we don't put too much power on those and fry them. And these here are, PC817s, and the resistors, I think, were about 100 ohms. Again, we'll cover that more at the wiring diagram in just a minute. But the idea of the optocoupler is that you can run some power through it on this side here, which runs an LED that then puts out light, right? Optocoupler, so optics, light, right? And then that couples to the far side where it has a light sensor that then completes the circuit on this end. So you end up having basically a non-physical connection between this half here and this half here. That's good because it means that these two are basically, they're able to communicate, but they're isolated. So if any voltage on here goes wonky because the plasma cutter something, I don't know, anything here goes wrong, then that voltage does not get over to these terminals, which are hooked up to the parallel port breakout board for the computer that's running LinuxCNC. So it keeps you from sending any potentially dangerous voltage back to your motherboard and frying the computer that's running Linux. So if you want to have optocouplers to do that last bit of communication for the up and down signals from here to your Linux. In fact, when I was first doing tests with this, I was using the Arduino plugged into the USB on the desktop, right? On my LinuxCNC installation, I was using the USB to power this. And not only was that a little bit on the low end, because a USB port really doesn't put out a full 5 volts, it's a little bit low. But a few times in testing, it actually made the LinuxCNC computer reset, like reboot, because it was getting noise from the plasma cutter coming back up to LinuxCNC. And after like the second time of that happening, I was like, oh, I should probably stop powering this off of the USB port from the computer, and that's why I have the separate power supply. Having a full-blown ATX power supply like this is possibly overkill. This is probably like a 100-watt supply or something dumb like that. It says here. I'm not seeing it. It's a lot of watts. It's a lot more watts than this guy draws. But the important thing is it's steady and it's separate, so it keeps all this stuff here isolated from the computer. Okay. It does all run still with the same ground as the plasma cutter, but that is okay. But having it go back to the computer, then you have more sensitive electronics you might mess up, right? Worst case here, if we fuck something up, we fry this board, where the Arduino, like this one is like $1 on AliExpress or eBay, whatever. It's not a lot of stuff to waste. And, while you might be able to do something wrong that ends up frying your plasma cutter, if you just be smart about things, you shouldn't do that. If you do, it's not my fault, right? Let's get that clear. You do this at your own risk, and I guess I made that disclaimer before. Yeah, but but you're probably not risking very much with a board like this, apart from stuff on the board. Like I showed before, I fried like 7 or 8 Arduinos. Like boohoo, there goes $7. At least it was a learning experience, right? A few more things to cover here. Firstly, I can't emphasize enough how much you really do want to have the separate power supply and how much you don't want to connect the Arduino to your computer via the USB. I know that'd be really handy to have just to be able to do the serial.print commands. That way you can do like debugging and monitoring and stuff over that serial connection. But you can't do that without bypassing the optocouplers and risking frying the computer that runs LinuxCNC. So, if you really wanted to, you could possibly fix that by taking the USB connection, splitting the wires out, putting an additional optocoupler on the transmit and receive lines, putting it back to the wire, then plugging into the computer. And that would work, at least in theory. They need to consider, how fast can your optocoupler switch, and can that keep up the baud rate your Arduino is trying to use? At least most debugging code for Arduinos runs the baud for the serial connection at like 9600. Not terribly fast, and probably any optocoupler would do. If you're running at a faster rate, like the 115,200 baud rate, that one might be too high unless you have particularly nice optocouplers. Things I haven't really tried yet that would probably work in theory, but they're really just a thing to do in the future. I haven't done it yet because, this setup, it works. But I guess if you did have that USB connection, you could do some other cool stuff too. Like try and tell LinuxCNC how big the difference between the arc voltage and the set point is. If that difference grows larger, you know that you are further and further off the target, and you could have the computer move the steppers, faster to have it, bring the torch down to the correct height or up to the correct height. Right now, the computer only gets a basic, like, you need to move up, you need to move down signal, but it doesn't know how far up or how far down or how fast it should move. So with some additional information over the USB, in theory, you could do that. And that would actually be pretty sick. I can't think of any other torchlight controllers that do something like that. But that's also work for a later time. Let's see. On here as well, another feature is that I put the Arduino on a set of pin headers, and that way it is removable. So when you want to update the firmware, I can unplug it, load the new firmware on, and then plug it back in. The reason for that being, when you plug it in the computer, again, you are powering it via the USB automatically, and that keeps you from running, having random stuff on here start up. This makes it a little bit less likely you're going to fry your Arduino when you plug it in the computer to do the firmware update. It does, however, make it a little bit more likely you're going to fry it as you plug it back in if you do it backwards like I did twice. You live and you learn, right? 2 Arduinos gone, mea culpa. Anyway, next thing is I am powering the Arduino and this whole board here off of 12 volts DC, even though the Arduino really only needs 5. There's a reason for that, okay? The reason being that I've read on the spec sheet of the Arduino that the maximum safe input voltage for these analog pins is equal to the input voltage you feed it plus half a volt. So if you power the Arduino off 12 volts, then it should be able to handle up to 12.5 on these pins without frying it. Now if you power it off 5 volts, it should be able to handle up to 5.5 volts without frying it. Now when the plasma cutter and the voltage divider output goes 0 to 6, that does mean in theory if you power it off of 5 volts, you might end up frying one of the pins with too high of a signal from your plasma cutter. So to get past that, I just use the 12 volts and then that should keep the Arduino safe. Now in either case, you're not going to be reading things above the analog reference voltage, right? They still get clipped above whatever you set that AREF to, whether it's the default AREF of whatever the Arduino's linear regulator is putting out, the external AREF you feed it via the linear regulator here on the board, or if you use the internal AREF of the Arduino, which we have not yet discussed. That's the next thing to cover, right? But by feeding it off 12 volts, you are theoretically making the Arduino a bit more robust against higher voltages from the plasma. I think. Pretty sure. Haven't fried any more Arduinos yet when running with the plasma, so, proof's in the pudding, right? Next thing is, as I mentioned, there's another analog reference you might want to try using on this Arduino, and that's the built-in 1.1 volt reference. So in your Arduino code, you can set a reference for the analog digital converter. In my code, I'm setting it to use the external one and then feeding the output from the linear regulator to that pin. You also have the option of using the internal one, which on an Arduino Nano is supposed to be 1.1 volts. On other Arduinos, that might be different. I think at least some of them run a 2-point-something volt, and then some of them have the option to do either, I think. It's been a while since I've read all the spec sheets, but it does vary from Arduino to Arduino. The trouble with using the 1.1 volt internal reference is that then you have to drop down the output from the plasma voltage divider once again, right? So that puts out 0 to 6, you need it in 0 to 1.1 range. So I was thinking at first I could just stack another voltage divider on top of the existing one, like a 6 to 1 divider. That would put the voltage in the range of 0 to 1, and it would do it without even clipping. So that'd be great, right? The problem is it doesn't work, because if you think about it, if you have a voltage divider like this one here, with these 2 resistors, and you stack another voltage divider on here with 2 more resistors, in reference to this top resistor here, it's now seeing these 2 in series as if they're added together, with the series resistor formula, and then these 2 added together, that new series one, with this in parallel. So the resistor here now sees less resistance beneath it, and that ends up changing the amount of this first voltage divider divides. You can't just keep stacking these things on top of each other indefinitely, because that's not how real analysis works in electrical engineering, right? There are things you need to consider as these circuits get more complex. So I did try that and then realized, like, oh wait, that obviously should not work. And that's kind of the beginning of where you delve into network analysis and Thevenin's theorem and all that more advanced stuff we're not really going to cover here. Now I was thinking I could possibly take the output from this voltage divider and to kind of isolate this from the rest of the circuit, put that out through an op amp. The op amp is an operational amplifier, which is a name that tells you nothing about it, apart from that it may amplify things, and hopefully it operates as you expect, right? In my case, it did not operate as I expected. There are a few different configurations you can use an op amp in. Again, I defer you to the EEV blog and All About Electronics, don't worry about those. But the short version is you can feed it a signal that's high impedance, so you can't draw very much current from it without disturbing the signal. And then from it, you can output something that's very low impedance. So you can draw more current from it without disturbing the signal. So if I did that and had an op amp here, then putting out the same voltage, just doing it, well, you can do a non-inverting one if you have a negative, details. If you use that to act as a buffer, right, on this voltage, then you could put another voltage divider after it. Or if you had it just acting as a buffer, you could also put the typical RC low-pass filter, where you pick your own resistor and pick your own capacitor, and you don't need to worry about the resistors in your voltage divider acting as a effective resistor in the RC circuit. You can pick your own, because the op amp then makes this V in to your filter kind of separate from the V out from the plasma torch. When I was trying that though, I was using the LM385 op amps in both those styles with the other voltage divider and just the RC filter. And I was running into some very strange issues where if I were reading the voltage off a battery, like a AAA, which is 1.1 or 1.5 volts, right? So you plug a AAA between these two terminals, that's lower than the plasma cutter put there. You know, plasma cutter is going to be more like 2.5, but 1.5 is still in the same 0 to 6 range. If I'm reading that, it would read it perfectly, no problems. But when I tried doing it with the plasma cutter, I would get all sorts of strange readings just all over the place. And I think that's most related to the LM385 not being able to handle the rate of change on the circuit, or on the signal from the plasma cutter. I don't have an oscilloscope, so I can't really test this, very closely and get a better feel for what is going on. But I do know there's a thing called ringing with op amps, where if you give it a like high frequency, very noisy signal, it just ends up making the signal even worse. And that is what I think I was experiencing in that case. So then I ended up just going the simple route and just doing the basic low pass filter with just the capacitor here, and then using the voltage divider as the resistor, effectively in this RC circuit. And that worked out, making things simpler and just ignoring, any possible application of the operational amplifier just ended up making it work for me. The next thing I want you to consider is that you could technically build this without the potentiometer or the LCD. Because the LCD here, all it does is display the voltage that the plasma cutter is putting out. And while that's nice to see to make sure it's like within a sane range, you don't need to see that. Like you don't need it. And the potentiometer, that lets you adjust the set point and then read it off the LCD. But you could even just hard code it as a value in the script that the Arduino runs. If you're like a sign shop and all you do is cut 22 gauge steel all day every day, and you never need to adjust the set point for your THC voltage, hell yeah, just hard code it, and that way you don't even worry about anyone ever bumping the knob here and adjusting it by accident. You could make this even simpler if you wanted to. Or if you had that USB connection with the optocouplers here to keep your computer safe, then you could adjust the set point and read the current value over that USB connection, and then even display it in the LinuxCNC console, which should also be kind of cool. Just making it as clear as possible. There's a million, billion, trillion different ways of doing this, and this is by no means the only way. And go crazy with it and make it your own. In fact, if you wanted to, you can even do the whole thing here without even having the Arduino. Because all this does is just averages a little bit off of the readings it gets from the plasma, and then compares that to the set point. So I'm pretty sure with like a couple of comparators and some other analog components, you could do that same comparison and then output up and down signals simply in hardware. Then adjusting your set point would be harder, because you definitely can't have the LCD if everything's analog hardware. You'd have like some series of switches or whatever, and that would adjust resistors and things to change the reference voltage you're comparing to, and it'd be weird. But you could do it 100% analog, and that'd kind of be cool, So, just a million ways to do it. And hopefully you're not too confused, because now we're going to head over to the confuser and take a look at the wiring diagram and the schematic. Here with the schematic for the THC. Again, I designed this thing in KiCAD, but here we're looking at a PDF copy of that schematic. So this is what I'm going to upload to GitHub and put links for down in the description below, and you can download it, open it up in any PDF reader. So, Events, Adobe, your web browser, basically anything now can open a PDF. And you don't even need KiCAD then, just to open it up and take a read. All the components in here should be pretty recognizable from the physical board we just looked at. So for example here, we have the 12 volt DC input and then the ground on that. And these two go to the labels of VCC and ground. And that way we can have the same label repeated across the board, like VCC right here, going to VIN on the Arduino, and ground connected to the Arduino ground. And then with those labels, we don't need to have as many lines drawn across the schematic, making it difficult to to actually read. So here we've got VCC, VCC, ground, 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 grounds galore all over the place. Okay. Over on this part here, we have the plasma input, both the positive end that goes to the analog read, that filtering capacitor, which again I found 10 microfarads works in my case. Again, you can make it pluggable and do some testing both on the breadboard and even on your finished PCB, just in case you find that some other value makes it operate a bit more smoothly. And then down here we have the connections that go to the DB25-1205 breakout board for LinuxCNC. Now in each of these cases, I drew it up with a set of screw terminals simply because they're convenient placeholders and kind of an easy way just to make the copper pads on the end product PCB that I solder those little jumper wires to go to the screw terminal blocks off of the board. I don't have the real screw terminals that match this and would go on the PCB itself, but they gave me a place to put the pads, and that worked well enough in my case. Now down here, this connector has 6 pins on it, because at first I was thinking about having some pins for like ArcOK and actually firing the relay from the THC and some other stuff I never really got around to. So of these 6 pins, really only these 3 matter, and then in reality it's going to a 4 screw terminal block, of which again only 3 matter. And then in reality, this guy and this guy end up being beside each other on the board. The next thing I want to draw your attention to is the LCD over here, which I did mention briefly before, but now I'm going to give you a bit more detail on what it is I'm using exactly. It's a 7-segment LCD, and it's one of the most brain-dead possible types. Okay, I found this part number here in the KiCAD libraries ended up matching the pinouts from the one that I had. It's a common cathode and then a 56-12 EWA. I guess, yeah, CC is common cathode, 12 probably means 12 pins. What's the 56 and the EWA? That I'm not so sure about. But the pins did match up, so I could use it here in the wiring diagram without having to make a custom part. I did find that the physical layout on the board here was slightly different, in that my pins ended up being 0.5 inches across, where this item in the library had the pins 0.6 inches across. So there I had to make the custom footprint, as I mentioned before, and that is one thing we're having problems moving the file from computer to computer because I am a KiCAD noob. But anyway, looking at the pins here, you will notice that the physical layout of the pins doesn't really line up with the way they're ordered here on the diagram. And by the same vein, here in the Arduino, they're also not lined up the same way. Like you got all the positive voltages here at the top, the grounds at the bottom, analogs all on one side, digitals all on the other side. That's not how Arduino Nano is really laid out. Okay, like these representations here on this image are a little bit abstract to help make the schematic cleaner and easier to read. And it's when you get to the PCB layout that they end up following the real pins over here. So you do your schematic in KiCAD, and then you come over to the PCB layout next. It helps you connect these things and kind of make sure all the traces go from one pin to the correct other pin. So over here on these pins, they order them by which segment they connect to. You know, segments labeled A, B, C, D, E, F, G, your decimal points, and then the way these super simple LCDs work is they have 4 other pins that basically multiplex, you know, to what digit you are connecting to at that time. So it's really a simple thing. You know, the one that you have might not be common cathode, it might be common anode. The pinouts here might differ, or you might have an entirely different LCD that ends up using a real communication protocol with the Arduino Nano, in which case it probably only has like 4 or 5 pins instead of the 12 pins used here, which is a hell of a lot of pins. But that all comes into play when you end up you know, doing the code for the Arduino, and in my case using the 7seg library and passing in the pins, pin ordering for that, or in your case using the other library for whatever, you know, if you have like an SPI connected LCD, you need to use a separate library for that. Yeah, things you kind of got to bumble through and test. And once you can do an LCD in one program, you can do it in this program, right? Let's see. So yeah, I basically align all these guys with the digital pins on the Arduino in a way that makes them wire up the traces somewhat cleanly, right? So basically doing a bit of manual fiddling just to get the things to go across easily in a way that fit in the confines of the copper-clad FR4 I had on hand. Now I will also point out I left the digital 0 and digital 1 unused because those pins are used for your USB communication. So when you want to upload a new sketch, you need to have these things free. Now if you use them for you know, other outputs and stuff, you can typically still upload new firmware by like resetting the Arduino and timing it correctly when you hit the upload button in the Arduino IDE. But personally I find it easier just to leave them unused if possible, and then use primarily the other digital pins. So that's what I'm doing here. Let's see, what else on that? I think that part is pretty good now. So let's talk about the linear voltage regulator I have here. Right, so this guy is an LM317, for which we have the spec sheet over here. Close that out. So basically it's a linear regulator where you feed in, let's see, does it have the range of the voltage input here? It takes some large input voltage and can output it very precisely based on the resistors that you add to it, as in this diagram right here. There's a little formula for your V out. It's 1.25 times the voltage, or 1.25 volts times 1, plus this resistor over this resistor. And then this factor over here is usually small enough that it can be ignored. So in my case, I wired that up using a 200 ohm and a 510 ohm resistor. So you do that math, that ends up giving you, what is 4.4375, I think, volts output, ideally. Now in my case, I measured that with a multimeter after the fact and found, due to just some small errors in these two resistors, I was getting 4.45 volts output out of my linear regulator. The important thing is though, that 4.45 volts I was getting out was very steady, and that I know what it was. So in my Arduino code, when I go to scale my analog read values, I know what I'm scaling them to. Now these two resistors, you can pick basically whatever values you want to scale the output voltage of your LM317. The only restrictions on that being that the LM317 has to draw a minimum amount of current for it to operate correctly. So you want these resistor values to be fairly low, something below a kilo ohm. To help you get something close to the output voltage you desire as well, you want these resistors to be fairly accurate. So you might have noticed on the board before, these resistors here were blue, and these ones down here were brown. That's because the brown ones are your standard 5% accuracy resistors, and the blue ones here are a higher precision 1% resistor. Not to be confused with the Bernie Sanders supporter. Slightly different 1% resistor. But anyway, bad puns. Yeah, and I'll also mention that the little rings on those resistors do correspond to the values they're supposed to be. But when I mention like this is a something resistor, I usually just use an ohm meter. And like I said before, I think these are 100 ohms. They ended up being 470. I had to look it up again just because I don't know my my ring color coding anymore. I knew at one point back in undergrad, but I have long since forgotten. And now I just use a multimeter because it's simpler and it's not ever wrong. Anyway, so yeah, looking at the LM317 spec sheet, we can get the function that tells us what our voltage output's supposed to be. And then we know we have a steady output voltage we can feed into our A ref pin. And that means when we're reading the analog signal from the plasma input, we're going to get something stable to compare it to. We're also going to use, let's see, the 1 microfarad and the 0.1 microfarad capacitors there as a bit of extra stabilization, both on the voltage input and the voltage output, because they're recommended in the spec sheet for the LM317. And for no other reason, probably don't even need them, but they recommend them, and I had them around, so I chucked them in there. Let's see. With the potentiometer, we're going to power this thing off of the same output as the LM317. This thing isn't going to draw much power at all. It's just a potentiometer. It'll have some, some resistance, so it's not drawing, boatloads of current from this linear regulator here. And basically all it does then is give us an analog value on pin A0 that we can read to adjust the set point of the THC. So we feed in the 4.4-ish volts we get from this linear regulator, and then we read the middle leg of that potentiometer, put the other leg to ground, and then as we twist that potentiometer on startup, it will adjust the voltage seen at this pin, which we then read in the code, and then adjust that to the operating range of the THC. Okay? All right, down here we have the plasma, and as described, the RC capacitor, right there, and that is really all we're doing for reading that analog bit. It's really, it's pretty simple right here. Now, if your plasma cutter doesn't have the voltage divider, you're going to have to put one of those on the board as well. So rather than having this pin 1 here come straight in, you're going to have that pin 1 come in. There's going to be a resistor, a second resistor, then going to ground, and in between those two is where you end up reading this wire here, going to pin A1. Now down here, we're using analog 2 and 3 for switching the up and down signals on these two optocouplers. Now, these signals for the optocouplers are digital signals, but we're using analog pins because on an Arduino Nano, basically, not every analog pin can be used as a digital pin, but most of them can. I believe it was pins 6 and 7 that can't be used as digital outputs. It varies though from Arduino to Arduino, and I might have that wrong. Double check me on the spec sheets. If you have a Nano, 2 of these analog pins can't be used as digital outputs. If you have a Uno, it might be different, or a Mega, or a Leonardo DiCaprio. They're all different Arduino Nanos, or Arduinos. You got to follow along the spec sheets for the one that you personally are using. But yeah, these pins then, when you write to them with digital, digital write, either for high or low. At low, they'll be at ground. At high, they'll be at 5 volts. The 5 volts that your Arduino gets when you feed in the 12 volts on V in here, that linear regulator steps down for 5 for the entirety of the board. It puts that 5 out here in the pin here, and it also can put out the 5 volts on each of the pins here and here. So we have 5 volts out. That's going to go to our optocoupler. I've chosen a PC817 because you can get like 100 of them for $1 on eBay. Basically, every component on this board here, if I haven't mentioned it, is like piss cheap. It's ridiculous. You spend like $2 and you get like 100 of each of them. You know, these LM317s, yeah, they're pennies a pop. So if you're making these things, you know, don't worry too much about making them wrong and, you know, running out of spares or whatever, because when you buy them, you basically have to buy a minimum quantity of like 10, 20, or 100 or whatever, because they're all so cheap. Yeah, you spend $1 and you get 100 of them. So yeah, these PC817s, we've got the spec sheet for those over here, and basically this talks about how it has, you know, that LED on the inside. They're really infrared LEDs, but in any case, a few important things to note are that the maximum voltage, the maximum current you can put through it on you know, on the input side here is 50 milliamps. So we can't just hook it up straight to the output pin, right? The same thing with a regular LED, right? If you hook a regular LED to your output pin in your Arduino, it's going to draw too many milliamps and fry the LED, maybe not immediately, but at some point in the future, it'll overheat and then die. So as part of that circuit, we got to throw in a small resistor just to limit the current draw by a little bit. In my case, I found, you know, if you do 470 for this PC817, it's got a forward voltage drop of 1.2. So if we have 5 volts feeding in, a forward drop of 1.2, then we take, what, 3.8 volts and 470 ohms. So a little bit less than 10 milliamps coming over this side of the optocoupler. Now 10 milliamps is far less than the 50 milliamp max of this optocoupler, and it's also enough that if we look at the, let's see, where's that? The current transfer ratio, right? So we're going to be somewhere in this range here, which means on the far side, the isolated side, it can transfer up to, you know, 4 times, you know, 400% of the, you know, 6, 7, 8-ish, whatever milliamps we're putting through it. So basically it means that since we're feeding it with a modest amount of current, but nothing too crazy, it will not die, but it will form a solid connection here, so that pin 2 can be tied to ground, or pin 3 can be tied to ground. Because you see the way this is working here, these pin 2 and 3 are hooked up to the two input pins on the DB25-1205 breakout board, and then both those are being tied to ground when the respective opto isolator is activated. So if you activate this opto isolator, then pin 2 here gets tied to ground. If you activate this opto isolator, then pin 3 gets tied to ground. And then LinuxCNC can detect that the input pin is tied to ground, and then move the torch either up or down accordingly. So let's see, things you might be adjusting here. Again, you know, this whole LCD subject to change depending on what you want to use. You know, the values for this LM317 here, you can tweak them as desired. I just aimed for something that was roughly 4 volts and change on the output pin, because that way we can get a decent working range. And again, there's going to be some clipping because, you know, the voltages we get from the plasma torch will be up to 6 volts, and here we can only read up to 4.5, but for our purposes the clipping doesn't matter. These capacitors here, the 1 microfarad and 10 microfarad, probably help but aren't super crucial, you know, and the values, since they're just basic bypass filtering, probably aren't super crucial either. Also, this whole 317 package, if you want to get a different linear regulator, I mean, you certainly could. You could just get a, you know, a fixed linear regulator as well. The LM317, though, is nice because it's a very well-known package, and there's a lot of other YouTube videos demonstrating how it's used. You know, they're very ubiquitous, very cheap, and then they're also adjustable. So when you buy a pack of 20 of these, you then have 19 extra sitting around. So when you do other projects in the future, you can have a good solid linear regulator for whatever voltage you need on that project. Here we want something, you know, around 4 volts and change, so these resistors happen to work. If you wanted something that was, you know, a 10 volt output instead, as long as you input 12 volts, you could pick, what would the math be on that? Shit, doing math. I guess you want to have what? 1.25 times like 8, so you want to have 7. You want to have this one be like 100 and this one be 700 ohms. In that ballpark, if I did my math right in my head. But you have options, right, for other things in the future. This potentiometer, really, its value doesn't even matter, right? Because all that matters is whether it's turned all the way, you know, how far along its throw it's turned. Because it will scale the full range from ground to the voltage output of this linear regulator just as you turn it that whole distance, and then give you a analog read in your Arduino code of the full 0 to 1023 range. For the optocouplers, again, you're free to pick basically any ones you work with this application. I just picked this one because it was, again, ubiquitous and cheap. And then the spec sheet seemed that it, you know, had a good, you know, current draw limitation, you know, 50 milliamps is plenty to work with, and when you're even giving it a fairly low amount of current, it is still able to transfer a large amount of current on the far side. Yeah, and then I guess for your Arduino, again, you're welcome to use any Arduino you want. You just gotta, you know, adjust the pins accordingly, and be sure that you're, you know, following along with all the restrictions, like you know, which analog pins can or cannot be used as digital outputs. So yeah, I think that's all for the schematic. Let's take a quick look at the PCB itself. So this is where things get messy, right? Because I'm working on a single-sided copper-clad FR4 board. When you end up working with like dual-sided boards and things, you have a lot more leeway to work with. But since I'm doing everything on the back side of the board, we end up having to like feed these traces under the resistors and shit like that, and it's kind of hairy. But you can see, you know, where these inputs for the plasma were coming in before, and then going to the, you know, the terminal blocks on the side here, and then over here we had the other terminal blocks, you know, for these optocoupler outputs. The headers where the Arduino went, the you know, all the pins and how that corresponds for the LCD. And then over here we have our LM317, the filtering capacitors for the power input and the output from the LM317, our adjust resistors, and then the resistors to limit the current going to these optocouplers. So yeah, that was a lot, but I think that covers things pretty well. I'm sure people have questions. If you do, feel free to put them in the comments below. Do try to give me, you know, good questions that I can, you know, well, if you ask good questions, you're more likely to get a good answer, right? Even if the answer is I don't know, I can try to point you towards the resources I come across that may help you learn it for yourself. Because yeah, this took a lot of research on my part, just because I'm by no means an electrical engineer. But hopefully the work I put into this and explaining it to you guys, you can follow along and you know, maybe learn or even improve and build off this design right here. Anyway, I'm going to sign off, but thanks for watching, and we'll catch you in the next video when we discuss the software that's running on the Arduino itself.